Well, good day, everyone. Uh, Today we're going to talk about wood. If you can read what you see on the screen, just to confirm the terminology, um, wood is generally around the world, in the English language anyway, is considered to be trees, and the term timber is used to refer to wood at any stage after the tree has been felled. In the US and Canada, they also use the term lumber, which refers to wood that has been processed or sawn. Again, just a quick reminder. I'm not going to go into this in great detail, but there's a simple kind of distinction, which is that evergreens are softwoods and deciduous trees are hardwoods. It's interesting that not necessarily all hardwoods are hard, if you see what I mean, or as dense as you think they might be. Balsa wood, for example, is a hardwood, so the descriptions are not entirely clear, but again I'll allow you to read this later at your leisure. Here's a kind of distribution map of hardwoods and softwoods throughout the world, and you can see fairly clearly that the northern hemisphere produces the vast majority of conifers, and the southern hemisphere produces the vast majority of tropical of hardwoods, which is interesting in itself, and I'm afraid I don't have the reason for that, but when we're thinking about putting buildings together, that map might be relevant. The other thing that's relevant is to timber is how sustainable it is. How much of it is the only renewable construction resource we have in the world, after all. It is the only renewable construction resource we have, and so how can we best use it? What you're looking at is actually a kind of growth chart for I think for mainly for softwood timber, and softwood timber is fairly rapidly growing, which is why we can harvest it at about 30 years, and certain kinds of tree grow in a very particular way, like straight, which is useful. Pine, for example, is a very useful tree for the construction industry. The majority believes that everything hard to comprehend must be very profound. This is incorrect. What is hard to understand is what is immature, unclear, and often false. The highest wisdom is simple and passes through the brain directly to the heart. I like this quote, but Victor Schauberger is important in the context of wood, in so much as he wrote a wonderful book called Living Water, which is actually, it's not on your bibliography because it's a little bit left field, if you like. The book, Schauberger was the son of a logger, his father felled trees up in the hills, and which is often the case, and sent them down to the lake, chopped them into logs, sent the logs down to the lake through things that are called log flumes, Flumes in the English language. And the flumes were little channels, if you made out little channels that you put the logs into, and they went down to the bottom to the lake. Now they, of course, though they would originally, you would think the quickest way from A to B is a straight line, but what happened was the logs, as they travelled down these flumes from the top of the hill down to the lake, would crash against the sides quite dramatically, and by the time they got to the bottom, only what is sort of something like a third of them were still in a decent state to be usable. The others had broken quite dramatically. Now, what Schoberger noticed was that that's not the way water likes to move. Water doesn't like to move in a straight line. He looked at rivers and around where he lived, and he thought rivers travel in, they can sort of meander. And he designed a log flume that wasn't a straight line, that meandered down from the top of the hill to the bottom. And they dutifully put the logs into that flume, and the logs travelled very happily down to the bottom in one piece. And this was the beginning of a very interesting series of explorations with relation to water that I won't go into in great detail at the moment, but it's worth knowing. One of the byproducts of this was that Schoberger designed a very nice plumbing system where the inside of the pipes had little deflectors in them that meant that the water travelling through the pipes didn't travel in a straight line. It spiraled through the pipe. So if you can imagine little fins built into the pipe, this minimized the erosion on the pipe because that's how water likes to move. So a very, very clever man. So logs is the first stage of timber, straight from the tree, of course. But mostly we in the construction industry used what we call sawn timber sections. And again, as you know, sawn timber comes straight from the tree. Something's gone wrong with my system. And at the logging mill, they are sectioned into standardized shapes. And again, you already know that you work with the grain along the long length of the timber in order to. You don't work against the timber, you work with it, because the fibers, as I mentioned in an earlier lecture, run linearly along the length of the tree, and we need that tensile strength. And so that's how the tree gets broken down. And of course, sawn timber is still used in construction. This is a Kruk frame, C-R-U-K frame, a very traditional way of, sort of an A-frame structure, very traditional way of putting a timber frame together. It's doweled, as you can see. There's no metal, there's no screws or bolts used in this particular structure. It's a very nice way of putting wood together. And then the next processing of timber, as again I know you already are aware of, is to plane it, is to put it through a machine that makes it much, if you like, planar, much flatter all round. And then of course you put it through another machine that can actually can profile the timber for you. Now, the majority of timber that we use in construction nowadays will be engineered, and that means that it will be processed. It won't be sawn timber. Yes, we will use this, but generally speaking, it will be engineered, and that means taking small sections of timber and reassembling them, laminating them together, doesn't it? So it's sort of interesting. Here is a tree. Here's wood in its primary state, and what's happening here is that we're looking at a cross section where a limb is growing from the trunk of the tree, and at that point where it's growing right there, you can possibly see that it's darker. There's a darker section. What's happening is of course it's going to cantilever from here. This is cantilevering. So it's stiffening. It's naturally becoming more dense in order to deal with that cantilever. Now that's fine, but when you cut that down, you will get a kind of general even distribution of loads and forces in the tree, and suddenly you will get what we call in English language a knot in the system, and suddenly it's a lot more dense. Now, to redistribute knots and to make any piece of timber sort of evenly able to resist load, you cut it into smaller sections, lots smaller sections, and you redistribute the knots so that they're evenly distributed around the section, and you will actually have a stiffer and stronger length of timber. Not only that, of course, if you're in an environment where you can only grow short lengths of timber for one reason or another, assembling, gluing, laminating timber together to make bigger lengths makes a lot of sense. So here's, you might know the expression glue lam, usually it's GLULAM, glue lam, which we put together beams and columns with. Here's some traditional glue lam. This is rather beautiful. This is actually a yacht mast. So glue laminated timber is not a modern process. It's been going on for a long time. This is a traditional way of putting yacht masts and spars together, because you need a particular shape and you laminate timber in a particular way. Even to make a perfectly circular section, here you can see there are two sections laminated together, and of course sometimes you need to take openings or take mass away from the timber. Here's a glue lam vault, a series of glue laminated arches, vaults. This is a Hopkins project actually, for a grandstand at the cycling velodrome, the open air velodrome in Herne Hill in South London. Really rather elegant use. I've never been sure whether these are strictly necessary to carry the cantilever. They probably are, but these were apparently there before. These are cast iron columns, as you can see. They're apparently already there for the old pavilion, and they wanted to reuse them. Excuse me. There you go. So here we have a complete, if you like, orthogonal structure made from glue laminated engineered I-section beams and glue lam columns. Interesting again, and I cannot emphasize enough that this process of doubling, which is going on here, and also this process of keeping timber off the ground with a nice scarf joint connecting down to the foundations. So that's a good critical detail. The doubling is important because you're taking mass away. You're reducing the amount of material that you use. We'll see this time and time again in structure, that by breaking it down into smaller elements. I nearly said elephants. Into smaller elements, combining those together again. You're making a space frame, and a space frame. The principle is works extremely well. Of course, the other lovely thing about glue lam is that you can laminate it into bending. So you set out your on a bench, you set out the curve that you need. You put your first strip, thin strip, you bend it into shape, you lock it into position. You glue your next strip, and actually the moment the second strip is glued onto the first strip, they lock together and the curve is made. The curve forms. It will not change then, it will not bend, and so on until you have a structurally efficient curve. Just to remind you, that's different to the bowstring structure, where you're actually putting timber, which is another interesting way of building timber structures, where you put the timber into bending by pulling on it, by putting it into tension and then locking it. And that's an interesting way. But this, once you've glued the second laminate, it will not change shape. You can also steam bend timber, by the way. I think this is one of the longest glue laminated sections that I have come across. And as I think I've mentioned before, bringing materials to site is a very energy intensive process. Wherever you're working in the world, it's always good to think, why can I source local materials and avoid all the energy that's needed to bring materials to site. But if you do have to do that, and you've got a relatively straight road, which I imagine you need in this place, the efficiency of building a long span beam, which this is going to be, could be to your advantage. So here's interesting project Pompidou Metz, using that principle of putting glue laminated sections into bending. Sorry, might be worth another look. I'll come back to this because this is actually this timber is held in tension by the shaping. This is not glue laminated in the way we're looking at just now, because again, here's the doubling. Can you see the doubling going on in both directions? And that's nice because you can kind of weave the material by allowing one direction of the weave to slot through the material that's going in the other direction. The edge beam is critical because that's what in a way sets out the overall structural logic of the building. The overall geometry is controlled by the edge. It's exactly the same with tensile structures. You know, the wire rope, if you like, along the edge is controlling the shape. So just to distinguish, so all of this, what we were looking at just now was what we call glue laminated timber, glue lam. Sorry, my computer's being very slow to react for some reason. Not reacting at all now. Oh, there we go. Apologise for this. So what I was going to say was that there's a distinction between, we have to make a distinction between the generic description glue laminated timber and a development of that which is cross laminated timber. So the difference is that when you're glue laminating what was traditionally known as glue laminated timber, the grain of the timber was always in the same direction. You're just cutting it into smaller sections and reassembling those sections to make a longer piece of wood. With cross laminating, you're alternating the direction of the grain. Can you see that's going in that direction, that's going that way, and that's going that way? A little bit like the tradition of plywood, I suppose. And what that's doing is that's now giving you obviously that's giving you strength in all sorts of directions. So it becomes more like a floor or a wall, more like a load-bearing panel. So I'm going to use the phrase cross-laminated timber for long planar sections, and I'm going to use the phrase linearly laminated timber for columns and beams. And I hope you can get your brains and mouths around that. Here's some more CLT, cross-laminated timber. More and more this is going to be the sort of way that we put buildings together. So now this is now a load-bearing wall made of CLT. It's actually a load-bearing wall. So we go back to that principle of kind of masonry, stone, brick, reinforced concrete construction, where you're carrying floors and walls off load-bearing walls. Here's a combination of the two. I don't know if you can see, there's a kind of, you can see the little knots in the timber that generally are redistributed, so they're evenly distributed around these sections. This is a nice project, but I will describe in a later lecture in more detail by Amin Tahar. And these are glulam floors. These are CLT, cross-laminated timber floors. It just shows you what's going to happen here is there's going to be, all of this is temporary structure. There's going to be some outer walls which are actually precast concrete sections, rather interesting precast concrete sections, which will eventually carry the floors. So there's some temporary engineering going on here, isn't there? All of this is going to disappear. Again, when you're looking at your own projects, think about temporary engineering. Think about this process of how it's going to work. They couldn't have put up the concrete walls first. It just wasn't practical. This is an awkward infill site, as it happens in Islington, North London. So what do we have to do? We put a temporary structure in. We build the CLT floors. Then we put the walls in place, and that's what the building looks like in the end. And there's a nice detail, I haven't got it here, sorry, which is the junction of the edge of the CLT, as you can imagine, with the edge of the CLT and the these precast concrete sections which make up the outside facade. Lovely, nice, delicate little project, very interesting. Of course, you again, a series of boards and sheets. I'm not going to go into this in a lot of detail because you know what these are already. Again, whoops. I want to just remind you that it is important that timber does need. Although it's of course the most sustainable material we have, it needs nurturing, needs looking after in certain ways. You need, ideally, in an ideal world, you would always enable timber to be well ventilated, to get air around it. It doesn't want to get too wet and it doesn't want to get too dry. It just needs it needs to almost be alive. So we use the expression seasoning. Okay, so even when it's comes from the sawmill to your local timber merchant, it's gone through a process already of where it's been dried. The water in the timber, the moisture in the timber, evaporates naturally, or it's actually artificially evaporated using kilns to heat it. And then we tend to add certain preservatives because timber is prone to organic infestation from fungus and from insects, and it's also, as I said, it's prone to being if it gets extremely wet over long periods of time and it's not treated in certain ways, it will rot. And if it's extremely dry over long periods of time, it will rot. So you do have to add certain things to preserve it. They can be chemical, they can be natural. The world is looking at all sorts of interesting ways of looking after timber naturally. Of course, timber is traditionally used for making boats, so there's no problem with using it around water. It's just how we do it. So there's some detailing that you do need to be aware of and you do need to think about, and that will be part of your way of thinking about the life of a building. Timber buildings need to be nurtured. You need to go back every so many years. You as an architect have to instruct a kind of a future for the building. How is it going to be looked after? How often and in which ways? So that's part of your job. And towards the end of this lecture, I thought this was quite interesting. This is something you might design, but of course it wasn't designed. It was a product of a couple of things, rather fun in a way, which was that on the one hand side, the timbers were not protected from were not cured properly at source. In other words, the moisture was not extracted as it should have been. So obviously as the sun moves around this building, there's a hot side and a cooler side, and gradually the timbers began to warp as the sun sucked the water away from them. That was exaggerated by the fact that there's I think it's a lead cladding which absorbed heat, solar radiation from the sun, and actually exaggerated all that. I quite like it because there's a project there, isn't there, for a building that can evolve its geometry over time. That you could design that into the structure, but anyway, it'd be quite interesting. Yes, and I think this is interesting because looking at timber as a resource, a very nice little project in London for a new concert hall. Everything that you can see here, all the timber work, and some of it is structural, as you can see, is actually holding up the roof, which is kind of waffle structure roof. You can just about see it here. Structural beams, structural columns, beg your pardon. Some of it is just is veneer and facade. Some of it is flooring. Everything that you can see in this image came from one tree. and it was a hardwood tree. And the reason we were reluctant to use hardwood is that it generally takes a lot longer to grow than softwood. Well, what do I know, 200 years for a nice piece of Mauritian hardwood. So you think seriously before you cut a hardwood tree down to use it for a piece of construction. Nevertheless, the architects involved in this project went to the forest and identified a particular tree, gave it a name, which you would. I think is it La Contessa, King and Contessa, yeah. You give the tree a name, and you harvest that tree, and you use it in every way you possibly can. So it's a piece of this isn't a piece of engineered timber, including the the veneer, even finely taking an edge off the tree to make veneers. That tree becomes an auditorium, and I think that is a very elegant, if you like, project, isn't it? Yeah. So I'm going to now move on to just a few points about connecting timbers together. While I think about it, I'll go back a second. While we're back on kind of generally, there are now hardwood timbers that I'm not sure whether they're being genetically engineered or whether they've just been discovered, that grow a lot faster, grow pretty much almost as fast as softwood. I'm thinking, for example, of tulip wood, which is also known as pear wood, grown in the USA, and they say they can grow a hardwood tree in 30 to 40 years, which is interesting. Now, if you look, I think if you look on the data sheets that we've provided for you on your Blackboard website, you will see links to, for one thing, there's a lot of links to very good timber websites. One is just a general database of all timber types. So that's interesting, because wherever you're working in the world, you can look at your local forest. So if you have got timber growing and think, what can I do with it? Can I usefully do with this timber? There's a very nice, there's a number of PDFs, including one from Walter Siegel's Self-Build, although that's a separate lecture which you can access online that we deliver on Walter Siegel. There's another very nice one. This is what reminded me of it, on the Endless Stair project by Alex de Rijker by ADRMM, where the PDF, there's a document that analyzes every material that went into that project and the whole process, and kind of does an environmental audit of it, really literally down to the glue that glued the timber together. Every single bit of energy that went into this Endless Stair project is audited. So that's very interesting to read, and it's the sort of thing that you might have to do or consider, as a model for the work that you're doing for us in your technical assignment this year. So yeah, just a few quick things now on how you join timber. Joinery, the traditional way. Interesting because it dates back. That's a scarf joint, by the way, joining timber end to end, which has always been awkward. That can resist pulling away, can resist tension, can resist torsion, and can resist compression. This is what, at least 1,000 years old. Chinese drawing, I beg your pardon, of timber joinery. The good thing, of course, about joinery is that you're just using the one material. We talk about dry joints. This is a dry joint. There's no glue, and there's certainly no other materials. There's no steel, there's no nailing, there's no screwing. So you're just working with the material itself. What an interesting way to put architecture together with dry joints. Oh, here's a scarf joint. Sorry about that. Oh yeah, here's another one. This is a nice detail on this scarf joint. So you can see if you try and pull on each end, it's going to resist the, to some extent the pulling. These dowels help. Often they'll put what's known as a butterfly joint in here, and that will be a hard. So this could be softwood, that'll be hardwood. Here's a dowel which is hammered in, and this is a lovely little wedge. And often they would use hardwood for this wedge. Once that was flush with the surface, as you can see, you'll get a circle and you'll get a rectangle of a slightly different color timber within that circle. I'm sorry I haven't got an image of that, but it's a very nice, very elegant way of joining timber. And there's a nice trick. So there's a lot of complexity in this, and that's a engineered timber version of the this is green oak, obviously using sawn timber, and here's the engineered timber version of it. By the way, there's also a you will see on the under your study materials there will be a PDF of a lecture from WEIGHAG, WEIGHAG, who are the biggest engineered timber manufacturers in Europe. They're in Austria, and you can have a look at that. PDF. I'm not going to go into too much detail here about metal connectors. I'm sure you're very well aware of them. Just reminding you of the importance of keeping timber off the ground. These are nice. They're called flitch joints, FLITCH, where you slice into the timber and make the connection. There's a pin joint that's doing that. Very, very nice detail. If you do have to use steel in your connectors, flitch joints, and that's actually from the WEIGHAG factory, where they're joining some huge curving glulam sections that are going to become vaults with a flitch joint, with the same kind of joint. They like to do this clever stuff where you end up, you've got steel connectors but you don't see them. We would like you to be thinking about these kind of details. This is interesting because again, there's a couple of things going on here that I've often talked to students about, which is this is the Downland project by Ted Cullinan, Edward Cullinan Architects, some years ago. It's a beautiful, you can see it's a barrel vault, but offset arches, and it's made from, again, you can see the doubling process going on, can't you, here? Because the timber can flex, these members are thin enough to flex. It's actually built flat. That grid was built flat on the ground, and then as you can see, it's propped up. It's gradually these pneumatic posts gradually push the vault into position, and then two things happen when it's up. One is it's locked at each connection by this detail. So again, as I've often said, it wasn't me that said God is in the details, Mies van der Rohe, but the architecture is actually this little node here, which locks the two. Well, it's the beautiful doubling of the timbers going through, and it's the design of this bespoke. And of course, at the ground level, which you can't see here, it's locked by there's a concrete foundation at each end, which of course stops the vault from splaying out in either direction. This is same again. This is a more modern version. This is Foster at Canary Wharf. He could have. This is a similar kind of vault, actually, similar kind of vaulted structure. These are simple engineered timber sections. Of course, you could have designed a big curved engineered glulam beam, couldn't you? But it's cheaper and more efficient in a way in terms of construction technology to just have square end, just have orthogonal square ends, simple sections, and all the work is done by that node where they connect together. That's the architecture again in this case. So I have a load of simple square sections. What you're looking at here, by the way, is ETFE pillows, the inflated membranes which are keeping the wind and rain out, and that's the air supply to them. So finally here, finally, how to join various ways of joining Bamboo, which is quite nice, isn't it? Kind of, well, you could join anything, can't you? It's in a way, there's the joinery, that's lashing, so that's the kind of yacht technology, isn't it? And there's the steel, there's the adding steel solution. Yeah, I think that is it. One more thing I wanted to show you very quickly, and this is not just about timber, but it is partly. This is a project by Structure Mode, which companies I have mentioned, engineers that do come in and give us lectures every so often. Jeff Morrow is their director, and Jeff, this is a temporary structure, so it's worth looking at just partly because of these nice screw piles that this is at the Dulwich Picture Gallery for a pavilion. Starts off with you can see a series of screw piles. That's taking all the load. Here's the timber floor. I beg your pardon, this is the roof, and that's what's beautiful about it. It's a series of trusses. Here's the doubling again. It's pretty light. It's using tensile membranes where it needs to. There's the old yacht technology. There's a turnbuckle. There's a lot going on here, but very elegant. The roof is built on the ground and then propped into the air on you can see very delicate steel frames that are holding the roof in the air. There it is. This is not glulam. It's a sawn timber roof, and quite cleverly the architects put mirrored glass on the steel frame, so it sort of seems to float. Yeah, nice little project. I think, yeah, that will be that for timber. So yes, wood, lumber. Thank you very much.